All right, welcome everybody. Today we're going to talk about lesson number 57. You'll see homework 57 listed at the bottom of the slide there. It's only those 4 problems. This is still section 4.5, so we're still talking about integration by substitution. However, today we are going to be finding definite integrals as opposed to indefinite integrals. So instead of using plus c for all our answers are going to be numbers. So first, a reminder of what it means to be a definite integral. In order to be a definite integral, remember that this represents area between the curve and the x-axis, so long as the entire region is both continuous and positive. Your answer to a definite integral is always a number. In order to find that number, you are going to have to remember the fundamental theorem of calculus. The fundamental theorem of calculus tells us that after we integrate, we're going to plug in the upper bound, which is b. We're then going to plug in the lower bound, which is a, and then we are going to subtract them. Not only are we going to have to rewrite the original problem from x's to u's, but we're also going to have to rewrite the original bounds from x's to u's. So take a look here at problem number 1. First of all, notice that the way that we know that this problem is different than the problems that we've done so far are the fact that we have a lower limit of integration and we have an upper limit of integration. We haven't seen those so far in section 4.5. So to start, we're going to go ahead and identify what we think u was. And remember that u is always the inside of the more complicated function. So as long as you've been keeping up to date with the lesson so far, I think it's pretty clear to say that u is equal to x squared plus 1. Please also note that in this PowerPoint, I've added a couple of blank slides since the problems can get a little bit long and I write a little bit big. So it's possible that sometimes the work will move on to the next slide. After you've identified what u is, go ahead and take the derivative of u is du. The derivative of x squared is 2x dx. And the derivative of a constant, still 0. Go ahead and solve for dx, which in this case would be equal to du over 2x. So that's the same as what we've been doing for the last couple of days, rewriting the variables in the problem in terms of u. Now we also have to take our limits of integration, 0 and 1, and we have to rewrite those from x's to u's. The way that you do that is by taking your u equals statement, plug in the top number, plug in the bottom number, and that's going to change your x values into u values. So if u equals x squared plus 1, and we plug in the upper bound, which is 1, that is going to give us 1 squared plus 1, which is 2. If we then plug in the lower limit of integration, which is 0, that is going to give us 0 squared plus 1, which is now going to give us a value of 1. All of those steps are needed for us to now rewrite this integration only in terms of u variables and also in terms of u limits of integration. So this is now the integration, not from 0 to 1, but instead from 1 to 2. Leave the x that was originally in the problem. Change the x squared plus 1 cubed to be u cubed. Plug in the value of dx, which is du over 2x, and then go ahead and try to simplify. As we've been seeing for all the problems so far, the x variable, again, cancels out. That should continue to happen until tomorrow's lesson. So if it doesn't, again, you know that you're making a mistake. That's going to go ahead and turn my problem into the integration from 1 to 2. Even though the x is canceled, notice that the 2 on the bottom did not cancel, which means this is now the integration from 1 to 2 of 1/2 u cubed du. You need to ensure that your problem is rewritten all in terms of u's and also in terms of u bounds before you go ahead and try to actually integrate. So now that I have the integration of 1/2 u cubed, I'm going to have to go ahead and actually integrate that. So I'm going to move to the next slide here just so I have some more room. So the way that you integrate u to the third, we're going to start by leaving the 1/2. You're going to integrate u to the third to become u to the fourth. Don't forget to divide by 4. We're no longer going to put in the plus c because of the fact that this is a definite integral as opposed to an indefinite integral. So if I go ahead and simplify that, that is going to give me u to the fourth over 8. I now have to evaluate this using the fundamental theorem of calculus, and I am going to evaluate it using those u values that I found on the previous slide. So in the previous slide, I wanted to evaluate this from 1 to 2. So plug in the top value, 2 to the fourth, over 8. Make sure that you're subtracting what you get when you plug in the bottom value, which would be 1 to the fourth, over 8. That is going to become 16 over 8 minus 1 over 8, which gives us a final answer to this problem of 15/8. So as you can see, a lot of the steps are the same as what we've been doing so far, rewriting the variables from x's to u's. But now, most importantly, you have to remember that you rewrite the limits of integration from x's to u's. So 15/8 would be your answer here. And let's go ahead and take a look at problem number 2. So problem number 2, the integration from 0 to 1 of x times the square root of 1 minus x squared dx. Your first order of business is always to identify whatever you think the u is. And again, the u continues to be the innermost function of the more complicated piece. So I think it's safe to say in this example that u is equal to 1 minus x squared. That means that du would be equal to negative 2x dx, which of course would mean that dx is equal to du over negative 2x. Not only are we going to change our variables from x's to u's, but we have to go ahead and change our limits of integration from x's to u's. So the way that we do that is we take our u equals statement. You're going to go ahead and plug in the upper bound first. So that's going to be 1 minus 1 squared. And if you do 1 minus 1 squared, you go ahead and get 0. If you plug in the lower limit of integration, you're going to get 1 minus 0 squared, which is 1. When you now go to rewrite this problem, whatever u value you got when you plugged in the upper value has to stay at the top. Whatever value you plugged in for the lower value has to stay at the bottom. So our next order of business here is to rewrite this as the integration. Notice that something kind of strange here happened. Notice that the values of the limits change from 0 to 1, now to 1 to 0. That's a little bit interesting. We haven't really seen any problems where that has happened, but please know that it's perfectly fine that it did. So start by writing the original x from the problem. Instead of the square root of 1 minus x squared, you're going to rewrite that as u to the 1/2 power. Dx is equal to du over negative 2x. Simplify. As we've been seeing so far, the variables continue to cancel, as they should for the remainder of this lesson. Notice that the negative 2 does not cancel, which means my final problem is the integration from 1 to 0 of negative 1/2 u to the 1/2 du. So now that I have simplified as far as I possibly can, I'm going to go ahead and integrate on the next screen. So on the next screen, I'm going to leave the negative 1/2. As you go to integrate u to the positive 1/2, 1 higher than u to the positive 1/2 is u to the positive 3/2. Don't forget to also divide by that power. And because I have 2 things on the bottom, of course, that means I'm going to be multiplying them. So do a little simplification here. Cancel out the 2's. That means that my problem is now going to be reduced to negative u to the 3/2 divided by 3. Make sure that when you go to evaluate, you're evaluating it with the new u values that you found, which remember that instead of going from 0 to 1, it flipped to go from 1 to 0. The fundamental theorem of calculus says you're always going to plug in the top value first. So when I plug the top value in here, I of course get 0. You're then always going to do a subtraction, and you're then going to plug in the bottom value. So if I plug in the bottom value, I'm going to get 1 to the 3 halves, which is 1, make it negative, divided by 3. 0 minus negative 1/3, negative negative becomes a positive, which means my final answer for this problem is positive 1/3. Remember, as always, feel free to stop the video, rewind, do some practice, or send your teacher a chat message if you have any questions. We have 4 examples in total, so we've got 2 more to go. For number 3, notice that we have some fraction action here, so we're going to have to make sure that we rewrite our problem with a negative exponent. But to start, we are again going to try to identify u. U is always the innermost part of the more complicated function, which in this case, u equals 1 plus 2x squared. Go ahead and take the derivative. Du equals 4x dx, remembering, of course, that the derivative of a constant is 0. That's going to tell us that dx is equal to du over 4x. Who remembers what comes next? Not only do you change the variables from x to u, but you're going to go ahead and change the bounds from x to u. So go to your u statement. You're going to plug in the top number. You're going to plug in the bottom number, and you're now going to find your new values of u. So let's go ahead and start by plugging in the top number, which is 2. That's going to give me 1 plus 2 times 2 squared. 2 squared is 4 times 2 is 8. Plus 1 is 9. If I plug in the lower value, which is 0, I'm going to get 1 plus 0, which is 1. Now that I have my new bounds for u, I'm going to rewrite the problem. Not only am I going to rewrite it in terms of u's, but I'm also going to rewrite it only in terms of positive exponents. So my new bounds of integration are 1 to 9. So from 1 to 9, leave the x that was in the original problem. Take the square root of 1 plus 2x squared, which was on the bottom, move it to the top, and write it as u to the negative 1/2 power. Plug in for dx, which is equal to du over 4x. Again, as we've been seeing, those x's cancel. However, we still have a 1/4, so we want to make sure that we keep that there. So this problem now becomes the integration from 1 to 9 of 1/4 u to the negative 1/2 du. Now that I have simplified everything down to u's, I'm ready to actually go ahead and integrate, which I will do on the next slide. So on the next slide, I'm going to go ahead and leave my 1/4. The way that you would integrate u to the negative 1/2, which would be to go to the 1 higher power, which would be positive 1/2. Don't forget to also divide by that power on the bottom. When you divide by that power, again, make sure you know that you are multiplying. If you go ahead and do a little bit of simplification here, you're going to get u to the 1/2 on top, divided by 4 times 1/2. That would, of course, become 2. So u to the 1/2 over 2 is my final integration. And again, remember, there is no plus c because of the fact that this is a definite integral, not an indefinite. This is an indefinite integral. No, this is a definite integral as opposed to being indefinite. So you're now going to evaluate, and of course, you're going to evaluate using those u bounds, which in this case is from 1 to 9. And the nice thing about these problems is they kind of work out. Remember, of course, that u to the 1/2 is equivalent to the square root of u, and you'll notice that 1 and 9 are both perfect squares, which is going to make this problem relatively simple to evaluate. So you're going to plug in the top number first. So u to the 1/2 becomes 9 to the 1/2, also known as the square root of 9, better known as 3 over 2. Always a minus. Now go ahead and plug in the lower bound. That becomes the square root of 1, which is, of course, 1 divided by 2. 3 halves minus 1 half is 2 halves, which means all that work for a final answer of positive 1. Last but not least, our final problem here brings a little bit of trig back into the mix. So here we are trying to take the integration from 0 to pi of the cosine of x over 2 dx. Remember that you are going to start always by finding u, and u is going to be the innermost piece of the more complicated function. So in this case, u is equal to x over 2. And more importantly, you're going to want to remember that u is actually equal to 1/2 x. If you rewrite x over 2 as 1/2 x, it makes it a lot simpler to remember how to take the derivative. So when you go to take the derivative, you're going to get du is equal to 1/2 dx. If you now want to solve for dx, you're going to go ahead and cross multiply. So you're going to get that dx is equal to 2 du. After you have changed all your variables from x's to u's, you have to go ahead and change your bounds. So I'm going to start by plugging in the upper bound, which is pi. If you now do pi over 2, that of course gives you pi over 2. If you plug in the bottom bound, which is 0, divided by 2 is, of course, still 0. We're now going to go ahead and rewrite the problem first with the new bounds. So this becomes the integration from 0 to pi over 2. This is the cosine of u. And then dx is equal to 2 du. So again, a little bit of simplifying here. This now becomes the integration from 0 to pi over 2 of 2 times the cosine of u du. So instead of being left with a number on the bottom, which we've had for the previous examples, we now have a number on the top. In order to integrate 2 times the cosine of something, you're going to leave the 2, and then you're going to integrate the cosine, which I'm going to do on the next slide. So as you go to integrate 2 cosine of u, again, you're going to leave the 2, and then you're going to integrate the positive cosine of u, and the integration of the positive cosine of u, use your green sheets as needed, is the positive sine of u. And you're now going to evaluate that for your new bounds, 0 to pi over 2. So as always, when it comes to trig functions, it's good to remember your friendly little unit circle, your quadrantals, as it were, 1, 0, 0, 1, -1, 0, and 0, -1. Should you not remember these, remember you can always use a calculator, but in this case, just make sure that you are using a calculator in radian mode. So you're going to go ahead and find 2 times the sine of pi over 2. So 2 sine of pi over 2. You are then going to subtract 2 times the sine of 0. So 2, the sine of pi over 2, go up here to pi over 2. The sine is the y value, which makes this 2 times 1. Minus 2, the sine of 0, go to 0. The sine is the y value, which is 0, which means your final answer to this problem is just a 2.